that it? Okay. Do 5 o'clock today. I will be assigning another homework that after today, hopefully today, you guys will have everything you need to address it after we go through stress concentrations. Okay. So we're going to get back to stress concentrations. So we just got done going through torsion of members, right? And power, and the difference between power and energy and work performed, right? Power is the speed at which we're able to conduct work. Stress concentrations, though, we're going to start by stepping back and going into axial loads, right? These are our normal stresses. Stress is force over an area, right? Axial forces. It's in chapter 5. We talked about the St. Venant principle, right? Effectively saying that we'll get stress concentration at the locations of applied loads, but those stress concentrations or stress variations across the cross-section dissipate pretty quickly, right? Essentially, once we get down the depth that is the width of our member, we've essentially realized a uniform stress distribution. I think we all understand, though, in the real world, right, we've got different things that affect our design. We've got to make connections. We want to make designs efficient, right? And our different systems require the fact that we want to vary our cross-section in a specific element. And so in some cases, for axial, for instance, right, we've kind of have these 3 different types of discontinuities or notches. We might put holes in our axial members. We might provide shoulder fillets where we transition from a member that's narrower to a member that's wider. And we get these stress variations based on the fact that we have these internal stresses. We call them stress trajectories. And they are parallel to max normal stress. So if we look at the notch, say we had a steel bar, okay? It was connecting 2 elements. And in the center of it, we had a notch. Maybe it slid into another element in our design, okay? And we put these notches in it, and you can see these stress trajectories, right? They've got to travel from our areas of uniform width through these notches. And in moving those stresses, we essentially magnify the stresses themselves, okay? And so that happens with our holes as well as our shoulder fillets. So you can kind of see this increase in stress distribution as we get around the holes, because we're effectively transferring the stresses that were initially at the holes, right? We've got to go around them. So when we get to the outside of these holes, essentially the concept is shear lag, which we won't get into this in this class very much, but it's the fact that these discontinuities are very short in nature, right? So we're taking this stress and we're quickly moving it around something. And so when we get to the outside of each of these discontinuities, we get this increase in stress distribution, right? Because we don't have, in this case, if this discontinuity was super long, right, we would get some uniform stresses happening thanks to St. Venant's principle. Because over a while, those stresses would dissipate and go uniform. But because we have a hole and not this long, super long notch, right at that transfer, we've got this peak in stresses. So we get this normal, these are our normal stresses. And we do all of these discontinuities because in the real world we have to make connections, right? We have to provide a means of transferring stress in and out of our elements. We might want to have some design efficiencies, right? The real world, we have the free market, so if someone can do it cheaper, they're usually going to get most of the work, right? So you don't want to waste materials. So if you don't need this wide of a material all the time, maybe you neck it down to save on material. And then maybe the system requires it too. Maybe it's got to go through some other elements in this overall design, and so we need to make this tension element smaller or neck it down. So we end up inevitably having these transitions or discontinuities in our material, and those create stress concentrations. So as I mentioned, this stress redistribution and movement of the stress because we're taking this uniform stress, right? And we're blocking its ability to transfer across this material evenly from one end to the other. We now have to go around this hole. And the fact that we have to go around this hole, if we were to look at a stress block, which we're not going to get into it too detailed, because we have to distribute it around the hole, doing so induces a change in stress. So now we're no longer just in this pure uniform stress case. We actually impose some shear stresses and other normal stresses on in our material as we go around. Okay, this can be incredibly complicated. Okay, a lot of analysis and modeling goes into this. Fortunate for us, there's engineers before us who don't want to do things twice. So what do? Well, they develop these really easy charts that you can, for simplified problems like we're going to look at in this class. Okay, there's essentially charts that tell us what kind of a factor or a stress increase factor we get based on the configuration that we have for say, axial loads, or we're going to get into torsion. So I'd say texts develop solutions for many cases and the solutions they provide are what we would call stress concentration factor. Denoted as K. And our K, as shown in the diagram, is our max stress over our nominal stress, or our max stress equals K times our nominal stress. So if we're able to calculate the nominal stress or the stress in the element at a given location, right, based on the geometry of our element, right? In this case, we have the axial load of the axial load in an element, right, that has a notch on both sides and radius. We can come up with what this stress concentration factor is, right? What's important to note here is this nominal stress. We have to be careful about calculating that. So as I mentioned, the nominal stress is usually what we're calculating. Okay. It's the stresses that are out here, out in these normalized uniform areas, whether it's the net section or the gross section. You just have to be careful because these prepackaged solutions are either based on the net or the gross section, and our text is all based on the net section. Okay. So if you look here and look at stress nominal is the axial load divided by little t times little d, right? Which is effectively the area through the notch, which would be our net area, right? So we're calculating our net stress as our nominal stress. And then it gives us a K factor, a stress concentration factor, based on that net section. So you're not going to calculate it based on the gross or the larger part of our axial member, but the smaller part, right? The part that goes through the notch. Same with when we look at the holes, right? This is a flat bar with holes. Whoops, don't want that. All right, flat bar with notch. We effectively are trying to figure out a nominal stress, right? Which in our case, as I mentioned, is based on net. And then we have our stress concentration factor, which is based on our ratios of some of our geometric properties. In our case, for the flat bar with a notch, it's our radius over our diameter, right? Or I guess not really a diameter, but the radius of our notch divided by the width of the net section. Okay, so depending on what that ratio looks like, right, we get to find ourselves on a curve, and each of these curves is based on the gross width divided by the net width. Right? So essentially it's telling us how much are we notching out of our member. So if we cut half of our member apart by putting a notch through it, right, where d is half, or little d is half of big D, we're essentially going to be in this 2.0, right? And if we're in this 2.0, then we're on this curve. Based on this curve, we would then find our position on this curve based on our radius of that notch divided by the smaller width of our section, or essentially the width of the section through the notch. And then from that, we could come across and figure out what our stress concentration factor is, K, right? Straightforward, kind of. Just looking up a bunch of stuff in tables, or graphs, I guess. So again, with axial members, we've got, as I showed, we have flat bars with fillets. Same thing. We've got our net section stress that we calculate. We can multiply that by our stress concentration factor to figure out what the max stress is, and that's all based on the geometric parameters of our element, right? What's our radius? What's our minimum width? What's our maximum width? And having all of those things. Whoops, shit. We can figure out our max stress as K times our nominal stress, knowing that we're calculating this based on the net properties, or effectively what they're showing us in each of these graphs. And then once we know this max stress, we can figure out, right? We can determine allowable areas or loads based on the material that we have. Right, so if we have
So K is given to us here?
K is in these charts.
Charts, okay.
Yep. So all of the y-axes of these charts is that stress concentration factor K. And we get that based on going into these charts, knowing our ratio of the radius, say in this case of the shoulder fillets, over the smaller width, right? It's the neck down width. And then going into the curve, right? We select the curve that's appropriate for our given scenario. And then based on knowing the x-axis location in the curve, we can jump across and get our stress concentration factor.
Can you scroll back up to the equation for nominal stress?
No. Nominal? Which one?
For the whole.
This one.
Yeah, thank you.
I mean, it's essentially just calculating what is the stress at this narrowest width, right? So the full width minus the smaller width, or essentially the width of the hole, times the thickness, that gives us the area alongside the hole. And we put the load over that area and we get our stress. And that would be our nominal stress. And again, as I mentioned, some other textbooks use the gross section as the stress. So they would be actually calculating what this is. And they would have the stress, this chart calibrated for this area or this nominal stress and give you a stress concentration based on that. But in our case, we're going to do it based on the net section, which is what these charts are calibrated for. So we're going to go through an example. What? These are in the notes. Aren't they in the notes? What's that? Oh, I mean, yeah. But it's recorded. I guess you can go out there and watch it. I didn't know if you were trying to get the chart itself.
No, I just didn't
Okay.
finish that whole thing.
Sorry. My bad. Okay. So we've got these three charts for axial loads. We're going to go through a shouldered fillet and hole example. Okay. So if we had this part, it was 20 millimeters thick and is made of bronze. They give us the yield stress for that. It said determine the maximum safe load P if a factor of safety of 2.5 with respect to the failure by yield is specified. Okay. So we want to sleep at night. We never want this thing to ever reach its yield stress, right? So we actually take the yield and we divide it by 2.5. Right, and that's going to give us our allowable stress. So we have a thickness equal to 20 millimeters. Our yield, they specify as 331 megapascals. I don't know if you guys have been digging through the text much, but if you go out to the appendix, under Appendix D, you could get this value. Lists tons of different materials and some of the material properties associated with them. Okay? If they just gave you this C86100 bronze, you could go out to Appendix D and get that value. Well, looking at this part, right, we have an applied load P that we're going to determine based on the allowable stress, which is based on our yield stress, right? And this element or part goes through two transitions, right? We have a shoulder fillet transition, and then we end up having a hole. So maybe we're making a connection at a bolt, right? So we add a little bit more material at the bolt hole, and then when we're out there in the extended section of this element, we don't need as much material, for instance, maybe. And so they've necked it down. So we've got 30 millimeters wide at its widest point and 60 millimeters wide at its narrowest point. So we have two locations. Of interest. So similar to problem 4 in the homework, right, where we had two limiting factors, right? We had our shear stress, maximum shear stress, and we had our rotation angle, right? Well, in this case, we have two locations of discontinuities, which are going to affect our maximum stresses. We're going to have two different stress concentration values as this force P transfers through this system. And so we really need to look at two locations of interest. And so we're going to calculate both and determine the limiting one. Right? And if they're asking us to determine the maximum safe load, yes?
So, wouldn't you be able to determine the minimum area at each point and use the one with the smaller minimum area as your limiting point?
No, because we are looking at the stress concentration values change, whether you're going through a hole or a shouldered fillet. And so depending on what the radius is and the other dimensional, like the diameter of the hole, all of those things affect how much peak stress we're going to see around these discontinuities. And that can overcome the simple approach of just looking at areas, right? Because you might have just as much area on the outside of the holes here, but the fact that you're drilling a hole versus having a shoulder fillet, that's gonna affect how much your stress gets increased because of this discontinuity, right? Transferring that normal stress, those stress trajectories around each one of these continuities. So it's a little bit more involved than the simple approach of just looking at areas. So if we start by looking at the fillets, right? If we go back up to our fillet chart, okay? Based on this chart, we need a couple things, right? In order to calculate what our stress concentration value is. We need our ratios, our little r, or the radius of our fillet over the smaller width of our member, and we need the large width over the small width ratio as well, right? Once we know what curve we're on and where we're at on the x-axis, we can back over and look at where we're at on the y-axis and get K, because really we're looking at this max stress, right? And this max stress that we calculate has to be less than the allowable stress, which is based on the allowable stress of our material, which was based on our factor of safety that they have imposed upon us, right? 2.5. So if we come back down here and we look at our fillets, one of those ratios was big D over little d. Big D over little d is 90 over 60. Whoops, so I write it backwards. 90 over 60. Millimeters over millimeters, unitless parameter, we get 1.5. We also have little r over little d. That's the radius of the fillet over the smaller width of our section, or 15 over 60, which is 0.25. So 1.5 and 0.25. Well, we've got this 1.5 curve, the red curve, 1.5. Is that where we're at? Yeah. And then we have 0.25. So we know we're on the red curve. We're going to go over to our x-axis value at 0.25. Then I'm going to take that and just follow it all the way over. And I'm sitting somewhere around here, right? Somewhere around there. I'm going to call that 1.73. So we know our max stress equals our stress concentration factor times our nominal stress. Well, knowing that our stress concentration factor is 1.73, it's essentially saying we amplify the stress seen in our material by 173% because we put these fillets in this material, right? The fact that it's got to work its way from the wider section to this narrower section. As we go through that section, moving those stress trajectories, we increase this stress or amplify it 173%, right? 1.73. Well, if we look at our max stress equation, we're told from the problem statement that we had a yield stress of 331 megapascals, right? and we wanted to provide a factor of safety with respect to failure by yield. So yield would be our failure stress of 2.5. So we take our failure stress divided by our factor of safety, that gives us our allowable stress, right? So we want to say our yield, which we've classified as our failure stress, right? If it yields, we've said it fails. We don't want it to fail, and we want to feel so good about the fact that it's not going to fail. We're going to put a factor of safety of 2.5 on it. So we're going to divide that yield by 2.5. So that would essentially say 331 megapascals divided by 2.5, or 132.4 megapascals, right? Newtons per millimeter squared. So that's the maximum stress we're allowing to happen here. We know the maximum stress. We know what our stress concentration factor is. Well, now we can come back and calculate the nominal stress, right? And we know that the nominal stress, in this case, if we go back up, it's in each of the charts. Because we're basing it on the net section, or the smaller section. Our stress is force over area, so we have our P, which is our load in our member, divided by the thickness times our smaller width is a small d.
Can you get it using the stress concentration equation?
Stress concentration equation.
K equals stress max over volume.
Yes, but we're ultimately looking at force, right? So we're saying stress nominal equals P over TD, T little d. We know what the thickness is, and we know what the smaller dimension is. We're really going to solve for P. So yeah, you could go through, figure out what stress nominal is, and then calculate this, but I'm going to shove it all together, and I'm going to say, now that we know what our nominal stress is, and we know what our maximum stress is, right? This is stress max. And we know what K is. We can plug all of these together. So I can say now stress max, it's 132.4 megapascals. And we're going to say that equals P over 20 millimeters times 60 millimeters times 1.73. That's our K value, right? This is stress nominal. This is K. And based on this, I'm going to solve for P. P comes out as 91,838 newtons, or 91.8 kilonewtons. So if we apply an axial load of 91.8 kilonewtons through this member, it will provide us with a factor of safety of 2.5 with respect to the yield stress of this material as it passes this notch, right? The shouldered fillets. But we don't not only have shouldered fillets, we have a hole in our member also. So we need to look at what's going on at the hole. Well, in that case, we've got little d over big D. Approximately 0.3. Right, if we go back to the hole, this one's pretty easy. We don't have multiple curves. It's just a function of little d over big D. So once we have little d over big D, we can go jump to the curve, run over to our y-axis, and figure out our stress concentration. So our little d over big D is 0.3. I am going to say that that equals 2.36 as my K. We again know that we have our stress concentration equation, or stress max equals stress concentration times our nominal stress. We know that the nominal or the maximum stress, we know K. Now I'm going to get the nominal stress in terms of the axial force like we did before, but in this case for a hole, right, this nominal stress equals P over the thickness times the overall width minus the width of the hole, essentially the net area. So this equals P over 20 millimeters times 90 minus 27. We can say that this, right, multiplied by the stress concentration of 2.36 equals 132.4 megapascals or newtons per millimeter squared. We can solve for P, 70.7 kilonewtons, right? Would have came out with newtons because we're talking about megapascals, which is newtons per millimeter squared. You divide this by 1,000, you get 70.7 kilonewtons. So now we have our two answers, right? If we're limiting our stress along each of these discontinuities to a factor of safety of 2.5 with respect to the yield stress of the bronze, okay? If we just look at the notch, we're able to run with or apply 91 kilonewtons or 92 kilonewtons through this section, right? And maintaining our factor of safety. But when we get to the hole, in order to maintain that factor of safety, we can only apply 70.7, okay? So the smaller of the two is going to control. So that's the right answer, right? Anything more than 70.7, and yeah, we're going to have a factor of safety with respect to yield of 2.5 through the notch or through the shoulder fillets, but we're not going to have that through the hole, right, or across the hole. All right, so that's axial stress concentrations. Similarly in torsion, okay? Same sort of case going on, right? We have elements where we need to, because of whether it's design efficiencies, making connections, or the design requires it, okay? Like a U-groove, this would be a U-groove. You see this a lot of times in pillow blocks. These are for bearings. Or thrust blocks, same thing. Right, where we had a shaft that's rotating and we need a place to maintain a bearing, right? A lot of times you put a U-groove in there, or if you have a place, like for thrust blocks, for instance, that you need to transfer axial loads while the shaft is spinning. Propeller is a good example of this, right? You put a thrust block in there, something that allows the shaft to rotate while taking out axial loads, okay? Stepped shaft. Good example of this is a pinion gear. Like ring and pinion, the differential of a vehicle. Okay. So it's very similar to axial concentrations. Except we're dealing with shear stresses. So in torsion, right, we have this shear stress max equation equals the torque times the max radius over J, right? Well, when we talk about stress concentrations, we have this stress max, which equals the stress concentration factor times our nominal shear stress, okay? These two are not the same thing. Okay? Not the same thing. So we have a shaft that has an applied torque to it, right? And it has geometric properties, it has a radius, things like that. We can calculate the maximum radius and our polar moment of inertia, which gives us the maximum stress in each of these shafts, right? The wider portion or the neck down or the U-grooved portion, right? The net section. But that maximum shear stress that we're calculating is not this maximum, right? It's really the nominal. This equation is telling us the maximum in the shaft, but as we go through a notch or a discontinuity, as we've found with axial loads, we get this increase in stresses. And so the nomenclature, for some reason, they specify them the same, but really this equation should just be the shear stress in the shaft at the radius, or tau C, but they denote it as tau max in the text, so that's what I'm going to keep. But just notice there's a difference. Right? We're going to be calculating our maximum shear stress based on applied torque out here or in the U groove, which we can do. Okay? But as we are passing through this discontinuity, we're going to even increase that stress even more based on the geometry of the U groove. Right? Again, our R over D ratios or D over D ratios. And so we're going to amplify that stress even more. So we kind of get like a tau max max. Okay, maybe that's a good way to put it. We're going to call this tau max max. Tau double max. Okay. Where this tau nominal is really the maximum that's one more U than needed. Maximum at the minor diameter. Okay? Like with axial, we use the net section or the smaller section of the discontinuity to calculate what our nominal stress was. Same thing here, right? The maximum stress at the minor diameter. So you're going to run through this equation and calculate the maximum stress or tau max at the nominal diameter. And then we're going to amplify that by the stress concentration factor, right? Where we have little d is our minor diameter, and big D is our major diameter. So we have U-groove, we have stepped shafts. Those are the two really common ones for torsional elements, okay? And on Friday, we'll start with this example.